relative stability from the Nyquist stability theorem, and with addressing the n equal to z minus p, and for stability, we're asking z must be equal to 0. That means no roots of the characteristic equations on the right hand side, and for systems, for the open loop system GHS, which has no poles on the right hand side, then for this case the P is equal to 0. So under the two situations, then we're asking n must be equal to 0. And n must be equal to 0, that is the situations like this. This is the real, the axis of the GH and open loop. And this is a measure of the GH. And so this n equal to 0 under the two spatial situations, that means this is the drawing and this is the minus 1, 0. That means z n equal to 0. So this is the omega approaching to 0, and this is omega approaching infinity, omega approaching to 0. So this is the portions of we plot here. And if you make the symmetric, basically that portion is like this. Okay. Under these situations, you can see this is the point minus 1, 0 is outside or not encircled by this plot. Okay. So for the situations we're talking about is this. Again, right now for these sections in particular, we focus on the two under the spatial situations, and that means the p equal to 0 here. And for many of practical control systems that fitting into this category, that means no poles of the open loop system on the right hand side. Again, for most of the control systems that falling into these situations. So we are okay to talk about this spatial condition. Actually, this spatial condition is very general in most practical systems. So again, for these situations, we call the system, if the system has no poles on the right hand side, we call the system, it's called the minimum phase system. Okay, so when we refer to the minimum phase system, and that means for these situations, okay, and again, the minimum phase system is pretty much general in most of the practical control systems, unless you work on the flight jet and like the F-16, that is in nature is unstable system, so that's a different story. But for most of the general practical systems, again, that is the situations. Okay, so now for the talking about the relative stability under the two situations for stable. For stable minimum phase systems, we must have the body plots like this. Again, this is one branch, and this is another symmetric one. So for most of the body plots, basically we only use one branch to represent this. Okay, and for a stable system, again, this is minus 1, 0. Okay, so now we talk about the relative stability. So for example, if this is the system 1, say, let me say G1, H1. Okay, and this curve corresponding, this is the real part of the GH, and this is a major part of the GH. Okay, so this is corresponding is the system 1, and let me draw another systems. Another system have the similar drawing, but that curve is like the green one we're showing here. Let me call it system 2. And so from here, we can have more quantitative comparison of the stability. So that's the reason why in this section we talk about the relative stability we can compare. So under this situation, you can see for the system 1, this curve is farther away from this critical point. the green one is closer to here. So we say this system is more stable. Compared to the green one, this one is less stable. The both systems are stable, but we can compare. Okay, so that means from here, these sections will allow us to do something. And under these situations, we can introduce different notes. So we can take a break.